Good evening and happy Thursday. There is a hand up. Yes. What's your question? Got you. Tonight we're going to start studying polynomial functions. The first question that we have to ask is, what is a polynomial? Right, function that has this form right? N is some positive integer. And each of the a sub I is a real number. Is a polynomial function. And again, we're going to assume that a sub n is non-zero. Right. Another way that you may see this written, and I'm probably going to write it this way, is just in summation notation, just so I don't have to write out all those terms. So each of the a's is a coefficient, right? So specifically, a sub I is the coefficient of the ith term. So n is the degree of the polynomial. And it's represented as degree of f, DEG of f. Right. So the degree of a polynomial is the highest power that appears in it. A sub n times x to the n is the leading term. A sub n is the leading coefficient. A naught is the constant term, or we call it just the constant. Now you can also call that a sub 0, but in math we just call it a naught. When trying to find the zeros of polynomials, these are very important. Being able to identify the leading coefficient and the constant. Right. Also, being able to identify the degree is pretty important. Okay. So that is what we're going to do for the first 6 problems. We're going to identify degree, leading coefficient, and constant. First off, the degree. All right, so remember, the degree is the highest power. All right, so we look at this and we go, okay, what is the highest power that occurs in this function? So that is our degree. I'm actually going to add in the instructions, also find the leading term. Right, yes, negative 2x squared would be the leading term, right? Negative 2 would be the leading coefficient. Oops. And then finally, the constant. It's 13. All right. Notice that in this case, the polynomial was not written in terms of decreasing order of the powers, right? All right. Doesn't have to be. Because remember, addition and subtraction. Well, I shouldn't say subtraction. Addition itself is commutative. When you write it in this form, right, where the powers are in decreasing order, we call that standard form. Let me double check that. I'm pretty sure that's standard. Yep, standard. Thought so. Right. So keep in mind, right, that means that your leading term is the first term when it's written in standard form. Otherwise, your leading term is the term that has the highest power. Right? That means you can't just blindly look at a polynomial and assume that the first term is the leading term, right? Right? Degree is 3. It's the leading term. All right, 14n cubed. What's the leading coefficient then? And what's the constant? Equals 8. Right, we already studied this type of polynomial, the one in number 1, right? That one's called a quadratic. Do you know what a degree 3 polynomial is called? That's not typically what we call it. a cubic. And so degree 2 is a quadratic. Degree 3 is called a cubic. I don't know how they came up with these names. Don't get tripped up with this one. What is the degree? What's the leading term? What about the leading coefficient? Be negative 625. What would the constant be? And this is why I said don't get tripped up. Be 16b to the fourth. Because look at the independent variable of the function. It's a, right? Right. But a is the independent of the function. Which means that while b may be unknown, it is still a fixed constant value. Exactly. Right. Now, you will study multivariate functions in Calc 3. Right, so the multivariate function is just a function of multiple independent variables. But not worried about that yet. What is the degree here? Where do you get 3? Where'd you get the 3 from? Well, you tell me. So again, you have to ask yourself, what is the independent variable of the function? So what is the degree? Degree would be 2. Right? This is a polynomial in P only. What's our leading term? Right? The leading term is 30p squared times m. What is the leading coefficient? Sure about that? Yes, it would be 30m. Again, because we're dealing with a function of P only. Meaning that while m is an unknown, it is still a constant in terms of this function. And what would our constant be? That would be 40m cubed. The constant would just be, right, so if I had something like this, then the constant would be 40m cubed plus 6, right? That entire thing is a constant. What's our degree? Right, degree is 2. Leading term? X squared. What's the leading coefficient? Right, leading coefficient is 1. And what's the constant? Constant is 4. Right? Degree is 5. Leading term? Right? Is negative y to the 5th. Leading coefficient? Negative 1. And what's the constant? Negative 4. Does anyone know what a degree 5 polynomial is called? It's called a quintic. A degree 4 polynomial is a quartic. So here are list of the common names. So degree 0 actually has 2 names. It's either the 0 polynomial right? Or it's a constant. Degree 1. It's called linear. All right, degree 2, we already know. All right, degree 3, cubic. Degree 4 is quartic. Or, as a special case, this I actually just learned. Biquadratic if all the degrees are even. Right, so it'd be like ax to the 4th plus bx squared plus c. Degree 5 is quintic. Again, we just saw that. Degree 6. So close. Sextic. Or you may also see it as hexic. Sextic is the more common. Degree 7. Yeah, 8 should be pretty obvious. Degree 7 is called, and for anyone in the medical field, this is going to be confusing. Called septic. Less commonly, heptic. Of course, in the hospital, you don't want to hear the nurse or doctor say you're septic. Degree 8 is octic. Degree 9. Nonic. Finally, degree 10. Close. Decic. Right. Once we get to 5, you can start to see the naming is pretty simple, right? Quin, prefix for 5. Sex is the prefix for 6. Sept is the prefix for 7. Oct for 8. Non for 9. And des for 10. Right, so if I say we have a tuple, right, that means it's a list of 10. Right, a non-tuple would be 9. Right, there are names for the higher degrees as well. These have to deal with the ordinal, the Latin ordinal number ending in IC. Right, so it looks like, if I look up the ordinal numbers, it looks like 11 is un, so it'd be an untic. 12 looks like it's duo, so it'd be a duotic. But yeah, we're not going to worry too much about that. Even most of these, we don't really worry about. The highest we really ever talk about is cubic. After that, it's just like degree 4. You very rarely hear it called a quartic. Right. Again, same thing. We typically just call it a degree 8, not an octic. So this is, again, one of those kind of like Jeopardy facts. Let's talk about end behavior. So if we think about end behavior, the end behavior is, how does it behave? What does the function do at the ends, right? So in this case, we'd be concerned with in this case, the function keeps increasing, right? It keeps going up. Or be the end behavior, right? So this direction the left end, or we let x go to negative infinity. Right? X approaches negative infinity. This end is the right end, or x tends to positive infinity. Okay, now, got to be careful. Infinity is a concept. It is not a number. It's an idea. So you can't like plug it in. Right? So for instance, this, if I say, what is f of infinity? That makes no sense. Weird things happen with infinity. Very weird things. One of the weirdest has to do with cardinality. Right. So cardinality is just simply the size of a set. So how much stuff is in a set. So if you look at the natural numbers, and we say, okay, the cardinality of the natural numbers. So how many natural numbers are there? What do you mean by a lot? Infinite of it, right? There's an infinite number of them. However, we've defined this cardinality to be, can I draw it right? I'm glad I looked it up. It's more like this. A left naught or a left null. So of course it's infinite. How many integers are there? An infinite amount, right? But wouldn't you think there's more integers than natural numbers? Right? Specifically, it would seem that there are twice as many integers as natural numbers because you're dealing with the negatives. This is not the case. They have the same cardinality. They have the same size. They do. But they have, those two sets have the same cardinality. And again, the same size. The reason is you can find a one-to-one correspondence from each integer to a natural number. And I'm not going to get too far into the depths of that because that is number theory. But that's the idea. So that's why they have the same cardinality. The rational numbers also has the same cardinality. That means it has the same size. The real numbers is the first we look at. Whose cardinality is not a left null. This cardinality is indeed just infinite. By the way, complex numbers are also infinite in cardinality. However, the cardinality of the complex numbers is larger than the cardinality of the reals. So the difference, to get technical, is the reals, the cardinality of the reals is not a left null because you cannot find a one-to-one correspondence from the reals to the natural numbers. Whereas with the integers and the rationals, you can. There is a one-to-one correspondence. Right. Think of a one-to-one correspondence as a one-to-one function. Because they're essentially the same. So notice what just happened then. Infinity is greater than infinity. Weird things happen with infinity. So there are actually levels of infinity. There's actually a really cool video on this. If there's time left over, I'll show it. Right. So again, this is all to say, and you're going to study more about infinities in calculus. But infinity itself is not a number. It is a concept, and weird stuff happens. In fact, the idea of infinity is relatively new. I think they accepted infinity in the 1900s, I believe it was. It's up until that point, mathematicians just thought there was a largest number. They just refuse to think of infinity. And by the way, mathematicians also used to refuse to accept the number 0. They would just not even think of it. So this is what we mean by end behavior. When we're talking about polynomials, I'm going to start with x squared, a quadratic. I don't know. Let's go with 2x squared plus 8x minus 3. Let's just go with that. For very large values of x, so let's say x is 100 googolplex. So Google is just a 1 followed by 100 zeros. All right, so that's a very large number. A googolplex is a 1 followed by a Google zeros. Right, so it'd be 10 to the 10 to the 100. Massively large number. Right, so large you probably can't even comprehend it. So I'm saying 100 googolplex. So 100 followed by a Google zeros. When you square that, it becomes even larger, right? What do you think happens if you subtract 3? It's insignificant, right? Oh, by the way, that 8x is also insignificant, right? Very common analogy that's used. You have $100 trillion in your bank account, right? 100 trillion. You drop $1 million. Does your bank account even notice? No, right? So for very, very large values of x, these terms really don't matter. The function behaves as 2x squared. By the way, for very small values of x, and when I say small, I'm talking about very large values in the negative direction, right? So like negative 100 googolplex. It's the same argument. This function is dominated by the leading term. And that is true for every single polynomial. For very large values of x on either side, the positive side or the negative side, it's the leading term that dominates the function. So it's the leading term that dictates how the polynomial behaves on the ends. We have two cases the degree is even or the degree is odd? Even degree. We're going to look at the power function x to the n. It's going to have one of two behaviors, or one of two general shapes. In both cases, it's parabolic. The difference is it's going to open upwards. Or is it going to open downwards? No, we're going to discuss the odd after this. Obviously, opening upwards, we know it's going to be if your leading coefficient is greater than 0. Opens downwards if your leading coefficient is less than 0. Right. By the way, what I drew was quadratic, ax squared, right? Specifically just x squared. Every even power has the same general shape. I'll show this on a math program. What all that changes is basically this region. It flattens out for higher powers. But the shape itself is the same general shape. So notice what happens. For a positive, on both ends, f of x is increasing without bound, right? F of x tends to infinity on both sides. In the case where the leading coefficient is negative, f of x decreases without bound. Right? So it tends towards negative infinity on both sides. Okay. Sadly, you do not have access to this program. Well, I mean, I guess you could if you wanted to buy a license. So don't worry about it. We're never going to use this actually in class. I'm only ever going to use it for demonstration purposes like I want to do right now. This is probably my favorite program. Yeah, let me do -10 to 10. Oops, I locked plot range also do 10 to 10. Let's go to 20. Change by 2 each time. So what this is going to do is it's going to show us the basic shape, or it's going to give us the graph of every power function from x squared to x to the 20th, but the even ones only, right? So it'll be x squared, x to the 4th, x to the 6th, x to the 8th, so on and so forth. Right? And I want you to look at how the graph changes as the power increases. Oh, why did it stop? Right. So as you can see, right, it's the same basic shape. What's happening is this middle part just flattens out, doesn't it? It's becoming more like, I don't know, a beaker, let's say. Right, so let's pause that. Let's look at odd degree, right? So ax to the n, I'm ignoring n equals 1 because that's just a straight line. So odd degree greater than 1. Again, we're gonna have two general shapes. All right, it's going to be one of these two. This here is if the leading coefficient is positive, and then the one on the right is if your leading coefficient is negative. Well, look what happens, right? as x goes into the negative direction, our function is decreasing without bound. Right? As x goes in the positive direction, our function is increasing without bound. That's if a is positive. If a is negative, it's the opposite. As x moves in the left direction, right, the negative direction, f is increasing without bound. As we move in the positive direction, f is decreasing without bound. I apologize for giggling. I just hear my son playing upstairs. It's kind of making me giggle, so I'm not laughing at you, I'm giggling at my son. Go to 321. So I'm going to do the same thing, except I'm going to look at the odd powers now. And again, you're going to see it's going to maintain the same general shape. All that's going to change is this begins to flatten out. Okay. What we'll do is now describe end behavior. Oh, I knew I forgot something. One more thing I want to look at. Once this goes away, once it catches up with the sink, that'd be nice. There we go. And that's the idea of turning points. Right. So a turning point is every time the graph turns. Right. So it's going to be a point at which the graph changes from increasing to decreasing or vice versa. So if we take a look, That's a good question. For polynomials, that can never happen. And we typically, I mean, a turning point is not actually the correct term. It's actually called a critical point, but you need calculus for that, so we ignore that. And this is the only time we use it, so I'm going to ignore the that goes constant. Right, so polynomials, the graphs have to be continuous and no jagged edges, right? They have to be smooth. So this would not be the graph of polynomial, right? Because there's a jagged edge there. But the graph I drew before that is a polynomial, right? Continuous, no jagged edges. It's completely smooth. So if we look here, here's a turning point. Here's a turning point. And here's a turning point. Has 3 turning points. So there is a theorem, there's a result for polynomials that states let f of x be a polynomial of degree n. Then f of x has no more than n minus 1 turning points. Right. Notice what this tells us. It doesn't tell us that it has n minus 1. It tells us it has no more than n minus 1. Right? In other words, the maximum number of times the graph of an n degree polynomial can turn is n minus 1. Which would make this graph, right? So what would the minimum degree of this polynomial be, right, for the graph that I drew? Right, it'd have to be at least degree 4. It doesn't mean it is degree 4. It could be degree 900. But we know it cannot be less than degree 4. Now let's look at the problems. Again, once my internet catches up and it allows me to sync. There we go. So these problems are going to describe the end behavior and then determine the maximum number of turning points. Right. Remember, when you're looking at end behavior, what you want to do is identify the leading term, right? Because it's the leading term that dictates the end behavior. What is our leading term? Now look at its power. Is it even or odd? It's odd. So it's going to be one of these two cases. Right? To determine which case, you now look at the leading coefficient. Is it positive or negative? It's positive, so yes, it was the left case. So that's the end behavior. Okay, so be careful. Maximum of 2 turning points, right? We don't know if it has 2 turning points exactly. And in fact, in this case, it doesn't. Right? Because this is literally just a transformation of a cubic. So just be a transformation of this. Has no turning points here. Right? Because it never switches from increasing to decreasing. Right? Right now, it is impossible to determine the exact number of turning points. Well, not totally impossible, right? Because for this one we can, because it's one of the toolkit functions, right? It's a cubic. That's a toolkit function, so we can tell. For the most part, it's going to be impossible for us to determine the exact number of turning points without graphing it using a graphing utility. However, in calculus, once you learn the derivative, you can then use the derivative to determine the exact number of turning points. In fact, that is a large part of the 3rd unit in Calc 1. Right, you'll be able to actually sketch the graph of any function pretty accurately using the tools of calculus. But for now, we can't do that. First, identify the leading term. No, it's not all of it. Right? Just a third x to the 4th. Right? I beat you to it. Sorry. Right, so x plus 1 to the 4th power, that's not in standard form. Right, you have to expand out x plus 1 to the 4th first, right? But since we only care about the leading term, all I care about, what's the first term of the expansion of x plus 1 to the 4th? x to the fourth, right? Now times that by that 1/3. That's why your leading term is a third x to the fourth. Right? Does that make sense? Now look at the power. Is it even or odd? Even, right? That means it's going to be one of these two cases. So now you just look at what is the coefficient. Is it positive or negative? Positive. So it's going to be this case right here, the one on the left. What's the largest number of turning points we can have? 3. Right? Degree minus 1. Negative a half x cubed. So what is f of x going to do as x goes to negative infinity? You'd have to take that into account. So you'd cube that as well before multiplying it by the minus 1/2. Right. So if it was 3, the leading term would be negative 3 cubed over 20. Negative 3 cubed over 2 x cubed, which would be negative 27 halves x cubed. Right, so what is f of x going to do as x goes to negative infinity? What about as x goes to infinity? Precisely. Right? That's the end behavior. And the maximum turning points we can have would be 2, right? So as x goes to minus infinity, what about f of x? That? What about as x goes to positive infinity? Say that. Which one goes negative? Oh, as it goes to negative, decrease. Okay. Like that? Precisely. And maximum number of turning points is once again 2. Leading term. All right, 3x to the fourth. All right, so what about as x goes to minus infinity? How is our function behaving? What about as x goes to positive infinity? So it'd be like that. Is there anybody who does not agree? Oh, you're disagreeing with yourself. Precisely. It's increasing on both ends, right? Power is even, and the leading coefficient is positive. Good. So what about the end behavior? Uh-oh. I forgot to do the maximum turning points on the last one. How many maximum turning points can we have for that previous one? And then what about for this new one? And it's the same. Degree is 4, so 4 minus 1 is 3. Are there any questions on polynomials? Okay. All right. Then let's go ahead, take a break now. When we come back, we will then look at dividing polynomials. So we will reconvene at 7:50. So we'll do 13-minute break. Okay. So continuing on, looking at dividing polynomials. First, let's look at what's called the division algorithm. Right? So this is used when we divide integers. What this says is for every integer, m and n, there exists unique integers q and r such that m is equal to n times q plus r, where r is between 0 and n. Q is the quotient. R is the remainder. right? We typically call n the dividend, right? And n would be the divisor. We can extend this to polynomials. Right, so for all polynomials f of x and d of x, there will exist unique polynomials q of x and r of x such that f of x equals d of x times q of x plus r of x. Where the degree of r is less than the degree of d. Q of x is called the quotient. R of x is called the remainder. Again, f of x would be the dividend, and d of x would be the divisor. Okay. Okay, now I have to wait for this to catch up. There we go. All right, so what we will do for this first set of 6 problems is find the quotient and remainder when f is divided by g. So if, or when you were asked in primary school, something like 237 divided by 4, what was the process you used? I don't know what it was called. Because I think they still do it. Does that look familiar? And then we go, okay, how many times does 4 go into 23? And then how many times does 4 go into 37? And so it's 59 with a remainder of 1. Remember what that was called? The entire process. Right, 59 is the quotient, 1 is the remainder. Long division, right? Does that sound familiar? So long ago. Feels like ancient times, right? Well, we have a similar process when we're dividing polynomials. Called polynomial long division. You take your divisor, right, and it goes into the dividend. Now, here's the game that we play. What do we have to multiply 2x by to get 2x cubed? X squared. Now multiply 2x minus 7 by x squared. And we subtract. Right now we're left with 10x squared minus 13x plus 5. Remember, our remainder has to have a degree that is smaller than the degree of the divisor. What is the degree of our divisor? Are you looking at the right term? All right, the divisor has degree 1. What degree are we left with down here? 2 is not smaller than 1, so we continue the process. So you play the same game. What do you have to multiply 2x by to get 10x squared? Plus 5x. Now multiply 2x minus 7 by that 5x. And then subtract. So 35 minus 13, 22. What is the degree that we're left with? Why would they both be minus? Right, but it's not minus 35, is it? It's minus 35. Right, so remember, this minus is going to be applied to the whole thing. So technically, it should be this. But those parentheses, to me, look messy, so I typically don't write them. What's the degree of what we're left with? 1, right? Is that smaller than the degree of the divisor? No. So we have to keep going. What do we have to multiply 2x by to get 22x? All right, so multiply 2x minus 7 by 11. Subtract what you get. 5 minus negative 77, 82. Wait. Now we're going to go with this, even though I wrote the divisor wrong. I don't know why I was thinking 7 instead of 3. Oh, well, I'll fix that right now. Once it catches up, but I did change that from 2x minus 3 to 2x minus 7. So we were asked for what? Quotient and remainder. Quotient is x squared plus 5x plus 11. Remainder is 82, right? Because the degree of 82 is 0, which is indeed less than 1. Why is that not changing? That's getting annoying. Whatever. Oh. Because I changed it on the wrong one. There we go. Now it's fixed. Why it keeps doing this? Where I have to restart it. Right. Dividend. I'm sorry, divisor into dividend. Not really. I do it to keep everything lined up. Right, but you don't have to write that 0x to the 4th there. Right, so we look and we go, okay, what are we going to multiply x cubed by to get 3x to the 5th? All right, so we'll get the 3x to the 5th minus 3x cubed plus 6x squared. Then we subtract them, we should be left with negative 4x cubed minus x squared plus 6x minus 6. Yes, okay. Is this degree less than the degree of the divisor? So we have to go again. What are we going to have to multiply by? Yes. So just look at the leading terms. So what are we going to have to multiply by, right? -4. Left with -x² plus 2x plus 2. Is that degree smaller than the degree of the divisor? All right, so we're done. Quotient is 3x² minus 4. Remainder is -x² plus 2x plus 2. Right. Also notice that when I wrote both the divisor and the dividend, I wrote them in standard form. Right? They have to be written in standard form for polynomial long division. All right. Excuse me for a minute. Okay. If our divisor is of a specific form, there is another method we can use, and it's typically easier. It's called synthetic division. This can only be used if the divisor has the form x minus a. Does our divisor fit this form? Why do you say no? Well, we can do that, can't we? So it does fit x minus a, where a is -2. So here's how we do synthetic division. Write out a. Draw a vertical line. Now look at the dividend. Write out the coefficients. Again, when written in standard form, it has to be standard form. So what are the coefficients? Be 2, right? 5, -10, and 9. First number just drops down. 2 times -2. Add 5. Times -2. Add them. Times -2. Add them. That's the remainder. These values here are the coefficients of the quotient. And the quotient has a degree 1 less than the dividend. So the dividend had degree 3. That means our quotient has degree 2, with coefficients of 2, 1, and -12. Q of x is then 2x squared plus x minus 12, and the remainder is 33. Can we use synthetic division? What is A? Now, what are the coefficients of the dividend? Like that? What's the degree of the dividend? Fifth power, fourth power, third power, second power, first power. Oh, we don't have enough terms. So what are you missing? Zero. So there is a cubed term. It's just not there. All right, it's not being shown. So shouldn't the coefficients be this? Be careful. Unlike with polynomial long division, where it doesn't matter if you don't write the missing terms, right? Like this first problem, not the first problem, the second problem. It does matter for synthetic. Right? You need the coefficients of all the terms. And the coefficient of missing terms is 0. First number drops down. Now it's just basic arithmetic. Times 4 plus 10 times 4 plus 0 times 4 plus 15 times 4 plus 18 times 4 plus -6. You're right. That's our remainder. Quotient. Right? Remember, the quotient has degree 1 less than that of the dividend. So it's going to be degree 4. And these are the coefficients. And then the remainder is just -206. If it's not in the form x plus a, or x minus a, I'm sorry. So would we be able to use synthetic? Be careful, because x squared minus 4 has 2 terms, and you can't use synthetic there. So synthetic can only be used with a linear divisor whose leading coefficient is 1. Right. So if your divisor is not linear, it can't be used. Can we use synthetic here? We can, right? A is 1/2. Our coefficients? 2, -5, 6, -3. Right, 2 drops down. Times 1/2. Plus -5. Times 1/2. Plus 6. Times 1/2. Plus -3. Quotient would be 2x squared minus 4x plus 4. And the remainder is -1. What about here? So synthetic, yes. And A is -2/3. Coefficients. 3, 8, -1, 7, 2. So 3 drops down. Times -2/3. Plus 8. Times -2/3 is -4. Plus -1. times negative 2/3 is positive 10/3. Now we have to deal with fractions. Plus 7 31/3 times negative 2/3 negative 62/9 plus 2. So it'd be negative 62 plus 18 all over 9, which would be what? Negative 44/9? That would be our quotient. Let me move it down. And then the remainder. Negative 44/9. Any questions so far? Okay. So if we re-examine the division algorithm, divide that entire equation by d of x, we get another way of writing the division algorithm. Right? We could also write it this way. Right? So notice that the instructions for the first set told us to find the quotient and remainder, right? Now we're being told to perform the operation, right? Or simplify the expression. So what this set of instructions is telling us to do is to use what I just wrote in green. Right, so we're going to write it as q of x plus r of x over the divisor. Right, so quotient plus remainder over divisor. Would we be able to use synthetic division? Yes, we can, right? What is our A? -4. And then our coefficients. 1, -2, -24, 15, and 50. One drops down, times -4, -2, times -4, -24, times -4, plus 15, times -4, plus 50. Actually, I might have enough room. We have x cubed minus 6x squared plus 15 minus 10 over x plus 4. Right? So this bit here is our q of x. And then this, with the negative, right, is r of x. We can use synthetic. Now we write out the coefficients of the dividend. And our dividend here is actually biquadratic. All right, 2 drops down, times -3 plus 6. I'm sorry, plus 0 times -3 minus 17 times -3 plus 0 times -3 minus 4. Right, then we're going to get 2x cubed minus 6x squared plus x minus 3 is our quotient. And then the remainder is 5 over the divisor, x plus 3. Once again, we can use synthetic. Right? A is a half. Leading coefficients. I'm sorry, not leading coefficients. Coefficients. 4, -10, 1, -1. Four drops down, times a half, minus 10, times a half, plus 1, times a half, minus 1. For x squared minus 8x minus 3 minus 5 halves over x minus a half. We can simplify that. Right? So what we could do is write this 5 over x minus a half times a half. Right? Or Multiply by 2 over 2, right, to get rid of the fraction in the numerator. However you do it, you're going to wind up with that being simplified to 5 over 2x minus 1. Any questions on dividing polynomials?